We recorded, that's good. Wait for it.
We don't want the whiteboard, we don't want this, we
No.
want this.
We want that, yeah.
Are you able to see the first slide?
Yes.
Great.
Excellent, excellent, okay. I think we're very close to starting. Screen sharing.
Would you like to do a presentation, David, or do you want to stay
What presentation is?
where you just see this instead of that?
Yeah, I think so, yeah.
Okay, so you're gonna click right here. Just come down to the little slide.
This one?
Yep.
Yeah, that's better.
Yeah.
Hello, everyone.
That's better.
This is Roland Winston.
So,
I'm chair of this. What?
We'll go back to the beginning.
I know. Yeah.
Okay. Go ahead.
Do you want to introduce
I
yourself?
do, but why the sound stopped?
Oh, we hear you.
Oh, you're waiting a minute? Waiting a minute. Okay. Okay, 1 minute to go.
We want to see your video. We want to see your video, right? Or no?
No.
Okay.
Anyway,
Well, what I mean is you want to be able to start it. That's what I mean.
well, I think we are starting. Okay. Now it's good.
All right, it's 2 o'clock, so I'll do the introductions, Holger.
Okay. It's yours.
So welcome to our fall physics seminar series. We have 12 exciting talks lined up for this semester. Our first speaker is Professor Roland Winston, who I've been associated with when I was his postdoc for 9 years at the University of Chicago. And at the time, he was doing a lot of work in particle physics and a lot of cutting edge work in optics, especially nonlinear optics. And today he's agreed to give our very first attempt to give an online physics seminar at our physics seminar series. So this is our first attempt at an online physics seminar, because last semester we just simply stopped our physics semester in the spring and canceled a bunch of talks that due to quarantine. But now we're coming back, and we're doing everything online for the physics seminar. And today, Roland Winston, a professor now at the University of California, Merced, is going to be, and he heads a few companies in solar energy. He's going to be talking about searching for a better way to concentrate light. So please join me in welcoming him. And also, if everyone could mute their speakers so that we get higher quality from Roland's speaker, the microphone, that'd be great. So welcome.
Thank you very much, Nick. It's been, hope everyone's well. It's been, I think, at least 10 years that I was visiting you and at Kansas State and gave a talk, and I enjoyed it so much that when you invited me again, I think I accepted pretty much immediately. So I hope people enjoy this talk as much as I enjoy giving it. So we're talking about concentrating light, and you might want to know, well, who cares? I'll try to convince you that it is important for both for kind of general culture, but also for technology. And the technology that particularly interests me is solar energy, which is rather important right now. I think it'll be important for the future as well. Okay, so we start with really the beginnings of light concentration. It was an application of Euclid. Everyone's heard of Euclid. These are pictures, of course. They're imaginary pictures. People must have just, I'm not sure how they got these images, but there they are. And what the connection with concentration was that quite a few years after Euclid's principles of using parabolas to focus light, there was a Greek named Archimedes, famous for many things, and in addition, he was famous for having set fire to a Roman fleet. And this shows a little cartoon of how he did that. He asked soldiers along the shore to aim their shields, and the shields had some curvature to them, at the sails of the ships coming in, and they set fire to the ships. And of course, that was, according to history, that was so surprising to the invaders that they let bring down their sails. Okay, so you might think that there's nothing new to say about concentration, since you're talking about more than 2,000 years. But there actually is some new things to say. So to continue, okay. So we asked the question that
So a way to explain that is to address the question of efficiency. What is the best possible efficiency? When we ask that question, we're going outside the bounds of a particular subject. Questions of this kind are more properly the province of thermodynamics. You can impose limits on the possible, like energy conservation, and the impossible, like transferring heat from a cold body to a warm body without doing work. And that is why the fusion of the sciences of light optics with the science of heat thermodynamics is where much of the excitement is today, especially in non-energy optics. For example, during the seminar I gave in 2000 at the Raman Institute in Bangalore, when the folks in India made me the solar Krishna leader in India at that time. That was a lot of fun for me. The distinguished astrophysicist whom people just called Rod, his long name, Brother Krishnan, he was a relative of actually the son of C.V. Raman. And it turns out that when I was staying at the Institute, he was in the audience, and he asked me a question: how come symmetrical optics knows the second law of thermodynamics? This provocative question from C.V. Raman's son served to frame our discussion. In fact, it also served to focus my mind, because I knew that we had a historic individual in our midst, and I better think carefully how I'm answering this question. So again, how come symmetrical optics knows the second law of thermodynamics? So to get back to the question at hand, let's do a very back of the envelope type calculation, that is called an estimate of the concentration of sunlight And it's what we would like to call a back of the envelope type calculation. So easy to follow and hard to disagree with. So it's a little cartoon of the sun and the earth, and you can make a right triangle. The radius is the radius of the sun, and the angle is the angle represented by the sun. So the first thing to notice is that the sine of the angle is just the ratio of the radius of the sun to the distance and the distance to the sun. It's a very small angle, about 1/4 of a degree. And what you can do is turn the concentration, which is the
What? Yeah, I think, well, they can figure the figures differently.
which is the turn the radius of sunlight falling on the surface of the earth, neglected the atmosphere, as just a surface the surface flux of the sun's surface compared to the flux of sunlight falling on the earth. And that's clearly the ratio of R1 to R2 squared, think about it a moment. And that again is pure geometry, because that's just the sine of the angle. And from that kind of consideration, from that knowing that you could not have a higher flux with any kind of apparatus as you could from the surface. As you could from the surface brightness of the surface flux as you approach the sun. For example, if you would just thought experiment, you measure the
This gives you time to process the equation. Hasn't stopped, has it? Okay.
If your face is moving, then you have it stopped.
so the radiance of sunlight as you leave the sun's surface and when you go back to the Earth, that's clearly 1 over distance squared. And at the orbit of the Earth, that's just 1 over sine squared theta. So 1 over sine squared theta times the radiance at the location of the Earth is the flux at the sun's surface. Now, thermodynamics forbids having concentration levels greater than the flux at the surface of the sun, because if you could do that, you'd have a brightness greater than that of the sun, and that's not allowed, again, by the second law. And by the way, if there's an index of diffraction, you have to multiply that by n squared, the index of the medium in which you're immersing your observation. So the concentration limit would then be n squared over sine squared theta sub s. And so we can bear those two limits in mind as we continue.
So if anybody has any questions, I'm happy to be interrupted.
Now, having established this plausibility that sine squared of the angle is a limit to which you can concentrate the solar flux. In other words, nothing you could do optically which would make it larger than 44,000 suns. And as a matter of fact, we'll see that this has been checked by experiment. It doesn't hardly need to be checked, but we have checked it by experiment just to see if we knew what we were doing. And we actually exceeded that number because we were doing the refraction. If you remember my remark before, the limit is the relative refract at the location where you're measuring the flux. It's n squared over sine squared theta, which for reasonable n squared is like 2 or something. You can get more like 100,000. So that's what you can do. So you might call non-imaging optics just a theory of thermodynamically efficient optics. And as such, it depends more on thermodynamics than on optics. I often tell my students to learn efficient optical design, and they should first study the theory of furnaces. That often reduces the size of the class pretty quickly. But if you persevere, and it's done wonderful things. Now we're talking about thermodynamics. So thermodynamics is a very interesting subject. It goes back to a French lieutenant in Napoleon's army. His name is Sadi Carnot. And He had fought Napoleon. But in 1824, he was a student studying physics in Paris. When I tell this to my class, I usually go on the room, see whether any sense of history, and say, well, how come by 1824 he was studying physics in Paris? What happened to his job with Napoleon, and a number of people generally recognize all the Napoleonic Wars were at least suspended, if not over, and Napoleon had been defeated by the British famously. Okay, so being a student in Paris was a nice let-up for Carnot, and he decided to think about what would be interesting problems around. And he seized upon the problem of how heat was converted into work with steam engines. Now this is the era when the steam engine was just coming into development, and in particular the British were very good at designing and building steam engines, and that was really the beginning of the Industrial Revolution, which so shaped human history from that point on. So he discovered that there was a relationship between how much heat and how much work, and the quantity that tied these together was temperature and something else which he called entropy. And that's how the second law of thermodynamics was discovered. And this was a discovery very more significant than all of Napoleon's concepts. That again is a personal opinion, but I back that opinion up by showing that. So I'm working it out this way. Remember, we want to tie energy to temperature. And in so doing, we introduce a new quantity which we call entropy S. So the magic formula is that if you multiply ds differential by temperature, that acts like an integrating factor, and it makes it a differential in both energy and PdV, which is work. Okay, so that's one way of saying the second law. Another way of saying the second law is that if you were to so this is arguably the most important equation in science. If you were to ask to predict what currently accepted principle would be valid a millennium from now, 1,000 years from now, second law would be a good bet. That comes from my Chicago colleague, Sean Carroll, who's now at Caltech. We can derive many things from this. One thing we can derive is that if you multiply temperature times the gradient of S, you get the force. This is called an entropic force, because it has to do with temperature and that's an entropy S. We can derive the second volt from the radiation law, that the radiation is proportional to 4 power of temperature. Then you get more interesting, guys. You can get information theory. That's Shannon and Gabor and now you're starting to include other fields. In fact, that's how the Allies won World War II by taking advantage of information theory. So You can go to astronomy and study the solar and explain features of the universe. For example, it's expanding, but how come expansion is accelerating? Which is an experimental fact. And even more, and much more modestly, you can design better, more efficient, thermodynamically efficient solar concentrators. This is why I'm here today. Let's talk about the limits of how much can you concentrate. Well, let's go back to sunlight. So sunlight, we know the temperature is 6,000 degrees. We know it's a black body spectrum, so we can consider it a good black body. But arguably, it's the most perfect black body in the sky. Well, the stars are over a large spectrum, good black bodies. You don't need to go to the sun to do that. You can simply get sigma to the fourth from both of them the solar surface flux is about 60 watts per square millimeter. So the one solar unit, the solar constant at the surface of the Earth is a little over a milliwatt per square millimeter. That's another good way to remember what sunlight, it's about another watt per square millimeter. The maximum concentration you can get, the 44,000, takes that back to the surface flux of the sun, the sigma to the fourth, which is some 44,000 times bigger than that. Now, of course, we have to make corrections. It's correct for the atmosphere. So the solar intensity on Earth typically more like a milliwatt per square millimeter, but then the atmosphere takes it over about 20-30%, and then we find out that this maximum 44,000 is one of a sine squared theta. So it hits you over the head. There's a deep connection between thermodynamics and the thermodynamics. Now, if you were to approach your friend on the street, a burglar man in the street, the suggestion how you might obtain the highest possible level of concentration is solar flux. A plausible response would be to just put us under the telescope, maybe like a 200-inch Collimator, which is not very responsive. San Diego, you probably saw it as you landed a little bit. Or whatever your favorite telescope might be. Of course, that's a thought experiment. You wouldn't dare from the telescope at the sun you would destroy it. So you don't do that. So you learn, if you're an amateur astronomer, you learn that lesson very early, either because you know it or because you stumble upon it and destroy your instrument. Okay, so if you do that, you say, well, I know how to do it. The best possible focusing device. Gosh, how can we do that? And that's the good old parabola. So if you look at a parabola, you make it to maximize the concentration. You find that the maximum is achieved when you have 1 over 4 sine squared theta. So that's theta at 45 degrees. Sorry, one line was 45 degrees. And 1 over 4 sine squared theta is more like 10,000, right? So, where is the four? Now, factors of four are significant in technology and many other forms of human endeavor as well. So, you can do a little bit of scribble, but it's a typical back of the envelope type calculation. And entirely similar considerations can be applied to longitudinal systems, call them 2D, the 2 dimensions, or trough concentrators. So if you do a straightforward generalization to a strip former, flat rather than district former, the limit becomes say kind of trough. The limit becomes sine squared 2 phi over 2 sine theta, which is just 1 over 2 sine theta for one angle of 45 degrees. That's the best case. So 1 over 2 sine theta instead of 1 over sine theta, you look at factor 2. So if you factor 2 for linear, factor 4 for point focus. In both cases, those are substantial factors. Where they're gone, are you making a mistake? Well, people's general reaction is, oh, you made a mistake. So I'm going to check your calculation, tell you where the mistake was, but there's no mistake. It's really true. If you go back to a more realistic type of two-dimensional situation, like a tube, you'd like to heat up the water in a tube, make yourself a nice solar heater. You find that the maximum concentration, the concentration ratio is 1 over pi sine theta. So the best you can do for theta is 45 degrees, right? Sine theta is equal. The best you can do for sine theta is 1. So theta is 90 degrees. We call it 90 degree rim angle. And the concentration ratio then is the best you can do for sine phi is 45 degrees. The maximum value is 1 over pi sine theta at that point. And you get 1 over pi as your 1 over pi sine theta is the 90 degree rim angle. So you fall short of the fundamental limit by a factor of pi, and that's the so-called pi effect. So that's something you can hold on to and amuse your friends with. Have you heard of the pi effect? And it's what the best concentration is for linear systems. And I mentioned linear because it turns out that the more practical solar devices are linear. So parabolic troughs are probably the most common. And they have the pi effect. So they're actually 3 less concentration than they could be, according to second law. So, to be honest, it was this desire to bridge the gap between the concentration achieved by common imaging device, the pi effect, and the sine wave concentration limit that motivated the invention of non-imaging optics. So this mismatch between what could be done and what was being done was what really spurred the whole subject. That's why we're here together today. Okay, so let's talk a bit about why conventional optics it ain't gonna work. So here's a paradox. Okay, suppose we have an echo chamber, which is has the following shape. Most of it is elliptical, and the other part is spherical. So it's a bit like a whistling gallery. So if you're the green person and there's another person at the red location, which is at the focus, one of the foci of the ellipse, and you're the center of the sphere, then most of the and you create a sound, there you talk. Most of that sound, if you're the green position, comes back to you. And most of the sound, if you're the red position, comes to the green position. So that kind of asymmetry means that if it's heat, and those are reflecting, those are mirrors, then if you heat up, say, green, the radiation from green comes back to itself, and very little bit goes to red. Whereas if you're at red, most of the sound, most of the energy, most of the radiation goes to green. So pretty soon, green warms up, gets hotter and hotter, red cools down. You have a temperature mismatch, but you haven't done any work. So you have the ability to collect heat without which would do work for you without doing any work. So you have an automatic refrigerator, if you like, or heater, and you know that can't happen. So that's why it's second law. So that's what people call a paradox. You know it can't happen, but it looks like it should happen. What's going on? Okay, so without trying to answer that paradox, which helps students. So that kind of motivates them to keep studying the subject, see what they can make out of it. So to summarize, non-energy optics is a theory of maximal efficiency of radio transfer. It's both axiomatic and algorithmic based. As such, the subject depends much more on thermodynamics than on optics. To learn efficient optical design, first study the theory of furnaces. Theory of furnaces. Let's consider enclosures, okay? Enclosures consisting of, let's do everything two-dimensional. So by two-dimensional, I mean that the infinite geometry is in the plane, and the other just are just boxes. I mean, they're walls. So you can have an enclosure like an oven. And the enclosure you can have 3 walls, you can have 4 walls, lots of other higher walls, but you really can't have less than 3. As you can see, then you're then no longer an oven, no longer an enclosure, it collapses. So just have to study 3 and 3, turns out. It's enough to study 3 and then we build up from 3 to the others. And this is due to we come up with formulas which are magical. They're called string formulas. And they're named Hodel strings after Hoyt Hodel, who was working on these problems at MIT just for heat transfer. And the calculation I'm about to show you is attributable to Hoyt Hollow. And he used the concept of a string, and these are called Hollow strings, which will continue out. Okay, so here's a drawing of a three-wall structure on the left and a four-wall structure on the right. And we're going to do some simple calculations with it. Now, caution. These calculations are so simple, they're back of the envelope. You don't have to do any calculations. You'll see. So all this has to do with, in the end, with concentrator design. So we ask ourselves, what's the best possible concentrator design? Well, let's do the three wall. If it's funny when you think it, the three wall case would be simple, in fact it is. And by the way, you can do 3, you can do 4. You can build up from that. So here's what you can do, and I've made the walls straight because I can never figure out how to draw non-straight walls, but that's the detail. So you have 3 walls, and I'm going to show you how to calculate these walls without ever doing any calculation, and not a serious calculation. Here's how you do it. So let's call Pij the heat exchange probability. So P12 is the probability that radiation starts at 1, ends up at 2, P13 starts at 1, ends up at 3, and then and so on and so forth. So there are how many unknowns are there? There's 6 unknowns, right? There's 3 ways you can choose the first wall and 2 ways you can choose the second one. So 6. So there are 6 unknowns. I need 6 equations. So 3 of them are just conservation of probability. Instead of 1, you can only go to 2 and 3. You can't go anywhere else. So there's 3 of those. And then the other is the second law. In other words, if you start at 1 and you go to 2, area 1 times P12 should be area 2 times P21, because, by the way, by area I mean length. These are all 2-dimensional, out of the plane. So that's the second law, because whatever energy goes from a pair has to go backwards in the same probability. So A1 P12 is A2 P21, and the 3 more. That's 3 more relationships. Now I got 6 relationships, 6 unknowns. You can do these back of the envelope type, and the answer is up the right. That's the answer. Okay. I haven't done a single calculation. Sort of neat. Okay, but you can do 3, you can do 4. So you just break up the 4 into 2 3s. So you're going to connect 1 and 4. Well, you finished the enclosure to add 2 and 3 walls, and then finish the enclosure by you put in internal diagonals to reduce the problem to two triangles. You see a triangle? There's 1, 2, 6, and 4, 5, 2, for example. So you can break up your units into triangles, but you've done the triangle formula already, so you can get the 4. So for example, you can get 1 to 4 quickly, and this is the so-called cross-string formula for radiated transfer. 1 to 4 is the sum of the diagonals, 5 plus 6, minus the sum of the non-diagonals, 2 and 3, divided by the normalizer by 2A1. I like to do this demonstration with getting a couple of students and then bringing some string and pair of scissors and a ruler and have them estimate, have them stand in front of the room and see if people can estimate how much radiation going from one student was flowing the other one. And they always get it wrong, very wrong. So we'll use a string to tell you how to do it. So you cut length of string, you measure out the length of the ruler, and then you do that cross string formula, and out comes the answer. Really no calculation. So that's called the string method. So having done a nice calculation method, we might say, well, good, that's good. Now we've got another chapter for our book. Let's continue. But we were not satisfied with that. We wanted to use this method not just to calculate, but also to design. And we wanted to design optical systems which concentrate by the limit from the limit limit. Another way, we can design optical systems that are maximally concentrated, and we use the string to do it. Now let me just show you how we do it. One way to show something is right is to just do it, show it. So you show, but you demonstrate by doing. It's kind of also the principle of some very successful teaching methods where the kids learn things by actually doing them. So here's a string method for designing a simple concentrator, which became known as the CPC, okay? And what you do is you use row string, as I showed you. You put the string on like a shower curtain. And that's shown in a drawing on top. And then you tie the string to one edge of B and B prime. You tie it to the edge of the aperture, and you hold the string to be tight, and you make it leave the slide. It's on a slider, like say point A. The string, let's start at point C. So the string starts at C, goes to A, and then goes back to B prime. And now you move the slide. You move the point C on the slider, and it's the same string. The same string becomes so basically it's CA plus AB prime, which is how you one end. The other end is A prime B plus B prime. So BB prime turns out to be then by right triangle. It's AC times sine of the angle theta. So A sine theta is sine C. Is BB prime. But hey, that's a sine law. You can choose the sine law with the old Holliston. Would have thought. Actually, I pointed this out to Hoyt Harville when I went to a seminar visit at MIT, and he was just delighted to know that his method of calculation had led to a useful design and construction. So, both happy campers. I was well, it's the young man, and for me it was a nice validation, but for him it was just a pleasure to see his work being used in a different application. So that was fun. Okay, let's just string up in action. Slider. And let's see, right. Stop. if we had gone any further, the profile, that locus of the blue, the locus of points where the string reflects, would have shown inward again, but then you lose concentration. So you stop it when the wall got vertical. Actually, in practical situation, you stop it well before that because you don't get much for the last 20% or so. The walls are almost vertical. So what happens? Well, you know what happens. You get the sine law. Okay, out comes the sine law. No tricks, just out it comes. So the concentration for a linear thing is 1 over sine theta, and for a cone is just square root 1 over sine squared theta. You've done it. Finished. So you might think of this as it makes the entropy condition an ideal concentrator, and there it is. And by the way, the rotation one has no reason to be, since the demonstrations in the plane, you might hope that the rotated one comes close, but it comes very close to the ideal, but not quite. And people are always working to improve it. In fact, at the last conference we had, there was a brilliant paper from I think it's from MIT, or I knew the person when he was at Zurich. He showed that for a rotated system, you do slightly better. I mean, parts in 100 better, maybe. If you numerically, if you just try to optimize it, and so it's good to know that it's a live problem still being pursued. Okay. And believe it, this is Dr. Cooper, I think. So if you have an index of refraction, that would be by n, and this is kind of tongue in cheek. When I give this talk, and people are skeptical, they should be, and they say, well, can this possibly work? Well, you can spend a lot of time working it out and see if it works, or you can just take the observation. If it appears as the cover of the magazine, they wouldn't put on the cover if it didn't work, right? So my tongue-in-cheek way of answering. Of course it works. So what now? It's especially useful to do these two-dimensional type constructions for shapes of the absorber that is not flat, more interesting. Two of the useful shape. In that case, you'll find that the aperture is 2 pi times the radius divided by sine theta. So circumference. That kind of sounds reasonable as it should be. So that's a useful design, and it gets used in illumination among other places, because you can take a tubular light source and turn it into a nice spot of light. So here comes. Putting it on home. Okay. Now let's go to the general concentrating problem. I want to take a radiation source, have an absorber. What should I put in the box to make it the best possible light collector or concentrator? So it's a simple thing to convince yourself of that the condition is going to be that you have to make the probability from the absorber to the source as high as possible, because it can't be more than 1. So P31 equals 1 is going to be the best possible concentrator, and that's what you want to put there. So that's the answer. You make your reverse probability over one. So that comes with a proof that it's almost self-evident. So take the probability seriously and make a reverse probability equal 1. You've done it. So that's it. So that's your principle. That's your design principle. And there's a rest. So when you do that, by the way, you find that so P31 equals 1 is the best you can do, and the maximum concentration in that situation, which is the ratio of the aperture to the absorber, is 1 over the probability of 2 on back to 1. Well, that's obvious, but it's true, and it's also useful for designing very efficient illumination systems. That's a different subject. Just turn on my work. Here's where the reverse beam nicely colored. But if you were doing it with parabolas on the left, it's very uncollimated. So instead of getting a nice crisp light beam coming out, it's all over the place. Now we'll just pause for questions. So time for questions.
All right, thank you for a very nice talk. It was at times a little bit difficult with the audio quality, but I hope everybody could follow along. Do we have questions? Just unmute yourself and go ahead.
So you mentioned that there was this limit of 44,000 for concentration. I think at one point in history you were demonstrating physically that you had 34,000 times the sun concentration. And did you ever go above that towards the 44,000?
We did. We went to 84,000.
Oh, okay.
We used the index of sapphire, I think. Yeah, we had a higher index. That's an excellent question. Yeah, we pushed it to about 84,000, and I think then the project ran out. Oh, I know what. I've made some bad calls in my life. One of the worst was I got a call from a gentleman from De Beer, and he wanted to supply us with a diamond, in order to boost our concentration. And I turned him down, which was so stupid. So that was a bad call. So we could have had the index of diamond, which is more than 2, I think. Yeah. But that opportunity, I'm afraid, is gone. Anybody else? So I might tell you that in our current research, and you're welcome to come visit, we're almost at the foothills of Yosemite Park. So we're a good place to visit because the park is so beautiful. Right now, the project we're working on is producing record amounts of temperature for linear systems. I think we're getting like 700 and some odd degrees centigrade, whereas the conventional parabolic troughs are under 400, and that's interesting. That's interesting for application. So once we're done with the getting it all set up and calibrated. We're going to take it to still in California. We're going to take it to a place called Plaster City, which is on the Mexico-California border, and they will put it into one of their furnaces, because to make plaster, they need very high temperature, dried out. Plaster comes out of the ground like mud when you dry it out. So actually get to try it out. This is always, just like experimental physics, just like Nick. I like to try things out. I'm not satisfied with just writing a paper, so we'll get to try it out. And these
Other
things,
questions from anybody?
and as Nick knows, these ideas are used, all over the world, in India and Australia and all kinds of places, Mongolia. So we do get them used, and that's always a lot of fun.
Yeah, I often go to the Vienna conference on instrumentation, and every now and then there's a lot of papers that are mentioning Winston cones. So yeah, it's nice to see some of their astronomical particle physics applications, which, just to remind people, I think, as you would agree, this whole idea started with your ZGS experiment at Argon Accelerator with a concentrator.
It did, yeah. You never know how things begin.
Or how they end, yeah.
Right. So I do appreciate this opportunity to talk to Nick again, and I do invite you to our lab once it's safe to travel. So hope we can get together in the not too distant future. We'll throw in a trip to.
Well, yeah, right now the problem is trips and traveling, so we'll survive this for a year. This was our first online seminar for the semester, and our first attempt to do an online seminar part of the semester. So we'll do a lot of learning. Our next talk will be Phil Lubin from University of California, Santa Barbara. He's going to be talking about the Starshot project of using a laser to propel small satellites to Alpha Centauri. And that'll be in 2 weeks from now. So everyone should join us again then. Thank you. Let's again give Roland a nice round of applause and welcome, thanking him for his talk.
Yes, thank you for that.
It was very nice. Thanks.
Okay.
All right. Have a good week, everybody.
Thank you.